All right, so we're back. And again, more history, which is probably your favorite thing, but honestly, this is the only history you'll have yesterday and today. So if you can make it through, we have a couple more guys to talk about. We have 5 more guys, and then we're done, and I promise we'll let you go. So, first guy is named J.J. Thomson. He was English. He did win a Nobel Prize, and if you look at up here, he again used the Crookes tube because that's everyone's going to be using the Crookes tube for basically from now on. So what he did was he basically played with this Crookes tube, the cathode ray tube, and what he did was he would add basically more electricity, less electricity, and then he would also play with magnets. And what he was trying to do was see, okay, like how much charge is it and how much mass does it have. So then what you would want to do was he was basically able to kind of balance this electric current and the magnetic field. And what you want to know, write it down, is that he found the charge to mass ratio of these cathode ray tubes. And what he later actually called them was an electron. So J.J. Thomson is really huge because he is the guy that said, okay, they're actually something smaller than an atom, and this is their charge to mass ratio, and they're actually something that's in the atom, and we're going to call them electrons. So, and then what he went on further to do is he actually said that when you look at all different cathode rays from all different elements, they're all the same, and every single one are these negatively charged electrons. So J.J. Thomson, he found this charge to mass ratio, which is a big thing. It was kind of the first numerical thing we knew about electrons. And then he also said, okay, everything has electrons, and they are something in the atom. And then down here, it's already written on your thing, but this is the charge to mass ratio. The E on top represents the charge, E for like charge, and the little m is mass. And what he found was that electrons have a big charge and a little mass, which makes sense. They're very small, we can't see them, but they do have charges that we can have static electricity that shocks us and stuff like that. So there is an actual charge to it. And you've probably never heard the coulombs here, and that's just if you go to physics, that's what they use for electricity. How much electricity is it? How much charge is it? And again, that's just a coulomb. So you don't have to worry about it, but just so you know it. And down here, you don't have to. You may want to know this, but no matter what metal, element, anything you use, the ratio is always the same. So electrons in gold are the same, they're going to have the same mass, the same charge as electrons in uranium or mercury or lithium, stuff like that. And that was what he got famous for. All right, keep going with J.J. Thomson. So this is good old J.J. Thomson. He looks very official, very serious. And this is kind of what he did. This is another drawing of the Crookes tube. You don't have to draw it or anything. But what he would do is he would actually have a certain amount, and he would measure how much electricity he was sending through. And then he would actually apply magnets to it that he could kind of change how much magnetic field they had. And he would see how much this would actually be bent. And he would look for this bending of the thing to actually figure it out. And then he had this thing called a phosphor screen, and if that sounds like phosphorescence, because that's exactly what it did. He wouldn't actually be able to see this necessarily, but he would see where it hit over here, and he could tell how much the beam bent, and from there he got the charge to mass ratio. All right, and then more about J.J. Thomson. He also saw that there was this other beam of particles that weren't near as large as the cathode ray, but they were there, that instead of going from the cathode, he saw that they were going towards the cathode. And again, if the cathode, we said yesterday, was negative, and they were going towards the negative, that meant that these things had to be positive. And again, he did lots of experiments that you don't have to worry about right now, but what he came up with was this proton. So J.J. Thomson is huge because he mathematically proved that there's an electron and that there's also a proton. And what he saw was he did get the charge to mass ratio for the proton, and you may want to write this down. It was smaller for the proton. So the proton has more mass, and it has the same charge as an electron, but opposite. So even though these guys, protons are usually +1 and electrons are -1, protons are heavier inherently. than that. And J.J. Thomson way back in, 1897 was able to figure that out. All right, and then very last thing that J.J. Thomson did, again, make sure you have that written down, so I'll give you a second if you need to. Last thing he did was he came up with another model. If you think back, we had John Dalton. He came up with the billiard ball model. Well, J.J. Thomson said that's not right now. We now know that there are little things in atoms. We have these positive protons. We have these negative electrons. So he came up with the plum pudding model. It's a really famous English dessert, so that's where it came from. And it's the second atomic model that we have. And it's just basically these pluses and minuses all smattered throughout. There's not like all the pluses are on one side and all the minuses are on another side. And up here we have uniform charge density and mass. What that means is that J.J. Thomson said that the charge was equally spread out through the volume. So if you think of our volume of a sphere as 4/3 pi r cubed, he said that, okay, we have the pluses and minuses are just equally spread. It's not like half the atom is positive and half the atom is negative. Everything was equally spread out. All right, and then last guy for this section before we take a little break is Robert Millikan. He's another American, which is, we don't have that many of them on here. But if you look at this, what he did was called the oil drop experiment. And really what he did was just, one, he took J.J. Thomson's work and went a little bit further. What he had up here is he had this thing, these red plates are actual like magnets, and he had these thing that basically broke down oil into almost atoms. And what he did was the atoms would start falling through here, and eventually he would change how much magnetic charge he had on the red plates, and eventually he would kind of levitate these oil droplets. Using this magnetic charge, because the atoms are charged. He would kind of equal it with these magnetic charges, and he would actually have these things basically floating. And you say, why in the world did he want to do that? Well, because what he wanted to do was actually figure out what's the charge of one electron. So what he did was he came up with one electron has this 1.60 times 10 to the negative 19th coulombs per electron. And again, remember, coulombs is how much charge. So it's just how much electricity is in that electron, and it's not very much, obviously. So the big thing that Robert Millikan did is he found out the charge of an electron. And then we said yesterday that Thomson did the charge to mass ratio. He used that and got the mass of the electron and the mass of the proton. So basically what Robert Millikan did is he used J.J. Thomson's results and went further. So J.J. Thomson had the charge to mass ratio, but he didn't know the charge and he didn't know the mass. What Robert Millikan was able to do was actually say, okay, this is the charge and then this is the mass. Again, it's basically he proved, again, just basically went along with J.J. Thomson that yes, electrons are negative and that everything has electrons. And again, he was basically going off the cathode ray tubes once again. So you don't have to write this down here, but basically, what do we find out from these cathode ray tubes, these Crookes tubes? It was a big change in the atom. First of all, we now know that atoms are divisible, not like Democritus, who thought they were indivisible. And then they did know that they're electrons and protons. That was kind of the big thing. All right, so take a little break, and then we're going to finish up history, and then you don't have to listen to the history of chemistry again.